what we want to do today is talk about, and part of the class, next class, is to talk about what happens when you have more than one wave traveling in a medium. Last week we talked about traveling waves. You only had one wave moving in a medium. We talked about the phase of the wave and a bunch of things about that wave, traveling waves, right? Now what we want to do is what happens when you have two waves moving in one medium. So this that you can find in Fizzlet is animation. Let's start with the first one. What we have here is two pulses. So we're sending this pulse, the medium. We're sending a pulse from the left, moving that way. We're sending a pulse from the right, moving this way. And if we do that in the same medium, then this is what happens. This is what you would see, right? This will be like independent. If you have one string and you send a pulse in that string, you have another string and you send a pulse going this way. This will be, if you do that on the same string, what's going to happen? Once they're occupying the same location in the string, the displacement of the string is the sum of the displacement produced by each one of the pulses. So you see that the peak becomes bigger than the peak here or the peak here. Is the sum of this and that height. So it's a behavior that is different from what you would expect if pulses in a wave were behave like balls, like particles, right? If you send two particles attached to a line, maybe two beads with a little hole, and you send them, they're going to hit each other. They cannot occupy the same space at the same time, so they're going to bounce off each other. That's what you would expect from particles. With waves, things are not like that, right? And the amplitude or the displacement of one wave adds up to the displacement of the other one. What's a bit more interesting is what happens when you send pulses that have opposite displacements. Right? One pulse is positive, the other one's negative. What happens when they overlap? They cancel each other. At some point in time, those two pulses have canceled each other. If they had the same shape, the same amplitude, moving in that way, then at this instant of time they cancel each other. But of course, that's not the end of the story. They keep moving through, passing through, and then you have them as if nothing had happened. Okay? At the time when they cancel each other, you might say, well, if the string is now in equilibrium, why would you expect anything to happen after that? Shouldn't the string just stay at equilibrium after that time? Why doesn't the string just stay like that? Now it's equilibrium, right? Anybody? If you have a string and it's flat and it's not moving, right? If you don't do anything to it, it's just going to stay like that. It seems like at this time, the two pulses cancel each other, they disappear. The string is not doing anything. How come the string somehow seems to start doing something again? The answer is that at this point, at this time, the displacement is 0, that's right, but the string has velocity. This point of the string on this side and this point of the string on that side, they do have velocity. We just took a picture of that time, right? When you take a picture, you cannot see that things are moving. They just seem like they're frozen in time, right? But the string actually had a velocity profile. And you can see that this point of the string, when it was flat, this point had some velocity. This oscillator here was crossing the equilibrium point, but it's crossing the equilibrium point with some velocity up. And this point, this oscillator located here on the string, an instant before, right, was crossing the equilibrium point, but it was crossing it with velocity going down. So the string is not just going to stay flat because, as I said, every point has a different velocity. And actually these 2 points, one has velocity this way, the other one has velocity that way. So then it starts to bounce back. All right?